In this final lesson, we're going to look at the atomic structure in the periodic table by using the periodic table to help us do electron configurations, determine ion charges, and then we're also going to talk about magnetism and paramagnetism. For the purposes of this year, we will not be looking at anomalous configurations. That will not be part of our evaluations this year. So the following diagram, as you can see, this is a periodic table. And as you can see, it has both the principal quantum number and the subshell listed. This periodic table, as it is organized here, helps give the order in which to fill the subshells. So personally, I actually find this periodic table, or the way it's arranged here, to be most helpful in filling out electron configurations. And I'll show you as follows. We'll look at it as we do the valence shell behavior. So looking at valence shell behavior, recall that valence electrons control the chemical properties of an element. Valence electrons are, as you remember, the electrons on the outermost shell. Therefore, only the outermost electrons, the highest principal quantum number, control the properties. The inner core electrons, those that replicate the preceding noble gas, they do not contribute to the chemical properties of an element. Chemical families share similar outer electron configurations, and that would make sense because chemical families react in the same way, and that's because they have similar valence, they have the same valence electrons, and so therefore they have similar electron configurations. So we're going to write the longhand electron configurations for lithium, sodium, potassium, and then circle the valence electrons. Let's start off with lithium. So this is where we will use this diagram right here. Lithium is located right here. So that means to get to lithium, we have to fill 1s. Don't copy this in. You don't need to copy this arrow. So we go 1s2 and then 2s1. Because we are only at this portion, we stop right here. So 1s2, 2s1. Scroll down. 1s2, 2s1. Let's take a look at sodium now. These are my alkali metals. Sodium is located right here. So to get to sodium, I go 1s2, 2s2, 2p6, and then 3s1. So just to recap, I need to get to sodium right here. The electron configuration would be 1s2, 1, 2, 2s, 1, 2, 2, 2p, 1, 2, 3, 4, 5, 6. So 2p6, and then 3s1. Let's write that out. 1s2, 2s2, 2p6, 3s1. Okay, if we do potassium now, I'm just going to erase some of these, some of this writing here. Potassium is located right here. That's my potassium. So I would go 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And so that is how we can use this diagram right here to help us do our electron configurations for atoms. Now the question didn't ask for just the electron configurations. It said circle the valence electrons. Well, remember the valence electrons are the electrons with the highest principal quantum number. So these are my valence electrons right here. This one, 2s1, 3s1, 4s1. And as you can see, they have similar electron configurations because in their principal quantum number, the highest principal quantum number for each of these, it only has the one electron. Moving down. Representative elements are those defined in groups 1 and 2 and groups 13 to 18. So these ones are considered to be the representative elements. These purple ones here and these green ones over here. In the middle, we have our transition metals, right? And these are the transition metals are sometimes called D block elements because their D blocks get filled as you progress across the periodic table. So any metal in here is filling up its D block of atomic orbitals. Okay, this right here, just as a side note, these are called your S block elements because they're the highest shell is the S shell, or the highest orbital is the S orbital. These are called your P block because the highest atomic orbital there is the P orbitals. Obviously this is your F block, and that is your D block. Okay, so transition metals are sometimes called D block elements because their D blocks get filled as you progress across the periodic table. So let's do iron. We have to find iron on the periodic table, and so let's take a second and locate it. If we were looking for iron, we would find it right here on the periodic table. 1, 2, 3, 4, 5, right here. This is where iron is. So if I would write the electron configuration for iron, I will go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, and that's where I stop. So the electron configuration, again, we've used this periodic table to the S blocks and the P blocks to help us figure that out. So iron was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then back to 3d, and it was 3d6. If I wanted to do the shorthand electron configuration, well, the filled inner shell here is this one right here. And that is the filled inner shell for argon. So I would write square brackets argon 4s2 3d6. You have to remember that the lanthanides and the actinides, they fill in these the 4f and the 5f shells. Okay, so you have to be aware that the lanthanides and actinides, they actually begin right here. So if you have an element that is located here on the periodic table, you have to remember to skip down to the 4f before filling up the 5d. So let's take a look at write the electron configurations shorthand for zinc and its 2+ ion, because we're going to be looking at the ion charges. Okay, so write the electron configurations for zinc and its 2+ ion. So if we look at zinc, right, the shorthand electron configuration, well, it has the inner filled shell of argon, and then it has 4s2, 3d10. Remember that when it loses 2 electrons, it's going to do so from its highest principal quantum number. So then the zinc 2 positive ion is argon 3d10. Now, lead, you will recall, is multivalent. It can form a 2 positive ion and it can form a 4 positive ion. Let's write the electron configuration for lead just for lead. Okay, so let's see if we can locate lead on our periodic table above. Take a second and see if you can do so. So perhaps you found it. Lead is actually located right here on the periodic table. So in order to get to here, I have to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then recall I have to jump all the way down here and I go 4f14, 5d10, back up, and then 6p2. So it's a bit complicated. Remember that the lanthanides are right here and the actinides are right here, so you have to jump down and fill those subshells. So we're going to write that out now. So electron configurations, shorthand. Well, if we look at lead, the nearest completed noble gas right here is xenon. So I'm going to do square bracket xenon, 6s2, 4f14, 5d10, 6p2. Square bracket xenon, and then it was 6s2. I had to jump down to the lanthanides, 4f14, 5d10, and then 6p2. This is its valence shell right here, 6s2, 6p2. So when lead forms a 2 positive ion, it's going to lose the 2 electrons in this subshell. Remember, it's got to lose them from the highest principal quantum number. So it loses it from this subshell first. So the 2 plus ion, which is, I believe, the most common form of it, is 6s2, 4f14, 5d10. If it goes and loses yet another, 2 electrons to make 4 positive, then it is xenon. And it would lose it from this shell right here. So we would have 4f14, 5d10. There are more sophisticated configurations that are not easily explained, but they require theories beyond the scope of this course and therefore not evaluated. So just to go over what we've covered so far, we are using this periodic table to help us do the electron configurations. We've learned what the S block elements are, the D block elements, and the P block elements, as well as the F block elements, which are your lanthanides and actinides. We looked at how the valence electrons control the chemical properties of families, right? These are within the alkali metal families. They have the same valence electron configuration. And then we did, we showed how ion charges were represented with electron configurations using shorthand configurations. Really, you do have to remember to, when you have elements that are located either in your 5D block or your 6P block, even so your 6D block or your 7S, you have to remember very carefully that once you get past this element, you have to jump down to the lanthanides and actinides if necessary. Okay, the last thing that we're going to cover today is we're going to look at magnetism, and magnetism is explained based on unpaired electrons in orbitals. So remember domain theory, or perhaps you remember domain theory. It was covered in, or typically covered in grade 11 physics. Effectively, domains are groups of atoms that have similar orientation, right? So the theory explaining ferromagnetism in iron is that unmagnetized iron, the domains of atomic magnets are randomly oriented. So when iron is unmagnetized, these domains, which are these groups of atomic magnets, they are all in different directions, right? And then when it is magnetized, the domains all line up in similar directions, right? And as a result, you now have a magnet, right? Because the magnetic domains are all aligned. There are three ferromagnetic substances that we are going to look at. Okay. The three ferromagnetic elements are iron, cobalt, and nickel. And their electron configurations are as follows. Well, they have argon, and then they have 4s2, 3d6. Cobalt is argon, 4s2, 3d7. And then nickel is 4s2, 3d8. Let's take a look at its d orbital filling in each of these cases. Well, if we looked at its d orbital filling here, it's 3d. We have the 5 orbitals. Remember the 5 orientations in 3D space. And we have 1, 2, 3, 4, 5, 6. Its d orbital filling for cobalt is very similar. It's like this: 1, 2, 3, 4, 5, and then we double up. Okay, here we go. And then for nickel, similar as well. 1, 2, 3, 4, 5, 6, 7, 8. What you perhaps will notice is that there are all these unpaired electrons here. Unpaired electron spins. In the first case, we had 1 paired and 4 unpaired. 2 paired, 3 unpaired, and then 3 paired and 2 unpaired. In these ferromagnetic substances, the magnetic properties of elements is a result of unpaired electron spins. So, magnetic properties are the result of unpaired electron spins. Okay, so magnetic properties are the result of unpaired electron spins. There are 2 types of magnetism: ferromagnetism and paramagnetism, and then there is diamagnetism. So ferromagnetism, its key feature is that it is a strong magnetic substance. And basically what happens is that the smaller atoms of these substances can act like tiny magnets and influence other nearby atoms to form domains. So in a ferromagnetic substance, you have domains because the smaller atoms influence each other, and they're arranged in such a way that they can influence each other and create these domains. These domains create strong magnetic substances. Okay? And the properties of magnetism are again due to unpaired electron spins. For paramagnetism, we have a weaker. Paramagnetism is weaker magnetic substance, so it's still magnetic, will still respond to a magnetic field. It's a weaker magnetic substance, again, still due to unpaired electron spins. Domains, however, cannot form. And because domains cannot form and they cannot align, this results in a weaker magnetic substance. Anything that is diamagnetic has no magnetic properties. All the electrons are paired. And if all electron spins are paired, well then it canceling the effect of magnetic spin. Okay. The challenges to the quantum mechanical model of the atom are as follows. There are basic concepts that are applicable in the macroscopic world that become inapplicable at the subatomic level. And also superconductivity, the ability to conduct electricity with zero resistance, is explained using quantum mechanics. However, the model sets limits for temperatures at which superconductivity takes place. And these limits are currently being exceeded. Therefore, the model must also have some inaccuracy. So even though we have the most up-to-date quantum mechanical model of the atom, there are still issues with this model of the atom that we are seeking to explain and refine. And so this concludes the unit on atomic structure. Please go over the notes and make some study notes for yourself. And by all means, please email me should you have any questions. Thanks for watching.